Um, Welcome to Office Hours. Today we're going to be going over Chapter 9. Chapter 9 has a few different topics, generally focused around momentum and conservation momentum. To start off, though, we have a topic called center of mass. Center of mass is whether you deal with like a mass that is distributed throughout space. Everything that we've done up to this point has been sort of implicitly a single point particle where all the mass exists at a single point, and we can do some physics, with that. Now, with center of mass, what we can do is we can adopt our physics that deal with point masses to masses that are distributed. In order to do that, what we need to do is find the center of mass of an object. So there are a few different ways to do it. One way that you'll see is if you just have like a series of point particles. Let's say I have, these are on like an XY, oops, an XY grid. And let's say that this is at 1, 0, 1, 1, and 0, 1. And let's say each of these particles has a mass m, okay? This is just a very simple example, obviously. Now, if I wanted to find the center of mass of these three particles, the center of mass would be something like the average in the somewhere in here. That would be the average position of those three particles. And the way that we find that average position in the center of mass is to do what's called a weighted average. You've probably seen this before, but in case you haven't, weighted average would look like this. If I wanted to find the x center of mass of these three particles, I add up the masses of each, which we say like m sub I. So the mass of each times the position of each, and then divide by the sum of the masses. So what that would look like for this very simple example that I've done, let's say I just want to find the x coordinate of the center of mass. I have three particles going to sort of, starting, I guess, with this one. The x position there is 1, and I said each of these particles has a mass m, right? So it'd be m times 1, whoops. And then I'd have plus, this particle also has an x coordinate of 1, so that would also be an m times 1. And then the x coordinate of my third particle here is 0, so it'd be plus m times 0, which will just be 0. And then I divide by the sum of the masses. I have three masses of mass m, so that'll just be 3m. What do you get here on top? You get 2m. On the bottom, you get 3m. And as we always want, since we're looking for a position, we want our masses to cancel, and they do here, and you get 2/3. So the x location of the center of mass point is 2 on 3. And if you were to do the y coordinate, you find the same thing. Now, this is for individual point particles. You'll notice that the center of mass is just a point in space. It doesn't necessarily need to be any one of those three particles. Again, it's just sort of the average that comes out of this equation right here. On the homework, the problems that you'll have to deal with will have to do with like plates. So if I have a plate of length, say L by L, where would what I want to do is I want to treat this plate as if it's a point particle, right? So I want to know this plate's center of mass itself. So long as the mass is uniformly distributed, the center of mass of the plate will just be right in the middle, which would be L over 2 by L over 2. And so if I have a series of plates, I'd have this center of mass of this plate, and this other plate would have a center of mass here. Maybe this plate is 2L by L on 2. In this case, I just take a half of the 2L and a half of the L on 2. So this plate is located, the center of mass of this plate is at L in the x direction, and L on 4 in the y direction. Okay, so let's take a look at a practical look at how to do a problem like this. So let's say that we have, let's go ahead and take a look at this diagram. We've got these 4 different plates that look like this. And we're given lengths for all these plates. We're not given exact positions. They are in an XY coordinate system, and ultimately we need to treat them each as if they are a point particle that exists at their centers, and we need to find XY coordinates for each of the centers. So let's see, let's label all of these lengths this length is 2L, this length is 2L, this length is 4L, 3L, 2L, 4L again, and then an L over here. And now in red, I'm going to write down the center of each one of these plates. So starting with the plate up here, starting with this one up here, I've got, let's see, it has a length L, and I know that there is a 3L length here. So that means that this Y coordinate would be 2L. It's going to go from 2L to 3L. So the Y coordinate for the center of mass there is going to be halfway between 2L and 3L, or 2.5, whoops, 2.5L. And then what about the X coordinate? Well, notice that the plate just has a length of 4L, going from 0 out to 4L. So I just need to split the difference of 4L, and half of 4L is just 2L. That's supposed to be a 2. Let me try it one more time. 2L. Okay, cool. So there you have it. Graphically, the center of mass for that plate would be right there, the tiny dot. Maybe I can make that a little bit better, but it'd just be the actual geometric center of the figure. And I just need to do this for each of the 4 plates. So for the upper left plate in the second quadrant here, the X coordinate is half of 2L, but notice that's in the negative X direction. So that would be negative L. And then the Y coordinate is half of this 3L, which would be 1.5L, and that's a positive Y. For this plate down here, the center of mass is somewhere right there. The width is not explicitly given here, but the width in the X direction is 2L because of the 2L up here. So split half of that. Again, my X coordinate will be negative L. My Y coordinate now is half of 4L, and that's going downward, so that would be negative 2L. And then we have this little plate down here in the fourth quadrant. And the center of that plate will be, this is just a nice square. Now the plate has a height of 2L, and we know that it terminates down here parallel with the 4L. So this would be from Y equals negative 2L to Y equals negative 4L. And split that difference for the Y coordinate, that'll give you negative 3L. And then what about for the X coordinate? The X coordinate is just from 0 out to 2L, so that's just L, half of 2L. Okay, so we have these centers of mass, and then in order to find the actual X and Y coordinates, I'll go ahead and do one of them. Which one will be more interesting? I guess we'll do the X center of mass calculation. Remember, what we're going to do is we're going to sum the masses times the X coordinates, and then we will divide by the sum of the masses. And yeah, okay, so let's just do it for each. Now, I believe these are going to have all the same masses. I think it's been a while since I've let me just, yeah, so we're actually going to need to also relate the masses. Yeah, right. Okay, so so the masses of these plates will also be different. The plate itself is uniform, which means the mass is evenly distributed over the whole 4 plates, but the mass will not be the same in each plate. What we need to do is calculate an area for each one. I'm not sure who's, as somebody could mute there. Okay, so we need to find the mass of each plate. Well, each plate is going to have an area. So in yellow here, I'm going to write down the area of each. In the upper right, we have 4L by L, so that's 4L squared. Come on, okay. Upper left is 3L by 2L, so that will be 6L squared. Lower left is going to be 4L by 2L, which will be 8L squared. And then lower right is 2L by 2L, which is 4L squared. What is our total area then? If I add all these up, my total area is 4 plus 4 is 8, plus 4 is 16, plus 6 is 22L squared. Okay, and so now what we can do is we can relate these areas to the total area, and we'll just create a ratio which will represent the mass since the mass is evenly distributed. All right, so now I can go ahead and go through and do the mass times the x position for each one of these plates, starting with the upper right. The x coordinate for the upper right plate is 2L, and the mass will be 4L squared divided by 22L squared. So 4 on 22 and times the x coordinate, which is 2L. And yep, and then we'll add for the next plate in the upper left, our x coordinate is -L, and our mass will be 6L squared on 22L squared. So that'll be 6 on 22 times -L. The positive and negative is important because you could be in the x or in the positive or negative x for your center of mass. Next plate, I'm going to run out of room here. So I'm going to, let's see, I'm just going to do plus down here. This is all, of course, on top of this fraction. The next plate is the lower left. For the mass of that plate, I have 8L squared on 22L squared. So that'll be 8 on 22. And the x coordinate is, again, -L. And then my last plate has a mass of 4L squared. So that will be 4 on 22 for the mass. And then multiplied by the length, I'm sorry, the x coordinate, which is just +L. All right, so all of that is the numerator. That's all the sum of the masses times the positions. In the denominator, I have the sum of the masses. Now, the way that I define my masses in terms of my area means that when I add these all up, 4L squared plus 6L squared plus 8L squared plus 4L squared, then what I will end up with is 22L squared on 22L squared. In other words, this is going to be a mass of 1, and that will be, yeah, just a mass of 1 total, just because of the way that I've defined it. Okay, and then I can, let's see, solve here. So 4 on 22 times 2 would give me 4 on 11L. So I'll have 4 on 11L plus 6 on 22 in the negative L. So we could actually do minus 3 on 11L. My next term is 8 on 22 times -L. So it'll be minus 4 on 11L. And then my last term is 4 on 22 times L. So that'll be plus 2 on 11 times L. And then, of course, divided by 1. All right, put these together. 4 on L, or 4 on 11L, and -4 on 11L cancel out. We have -3 on 11L plus 2 on 11L, which gives us -1 on 11L. And then on the problem, they give you some L, and you could solve from there. The calculation for the Y is going to be similar. So I'll go ahead and leave this here, but that's sort of a walkthrough of how to find the center of mass for a distributed mass like that. Okay, this problem is a little bit of a silo. You're not really going to have to deal with spatial distribution of mass too much. It's kind of just a first problem to get you going. The types of center of mass things that you may need to do is more like in the second problem. In the second problem, we have 2 stones. They have 2 different masses, and now the mass is important because they're going to ask us about the displacement of the center of mass and the speed of the center of mass of the 2 stones. So we have 2 different masses and 2 different release times. So just as we did back in the motion chapter, split your problem up into two. We have a first stone, which has a mass of, call it just M. Maybe we'll call it big M to indicate that we're dealing with a constant. And we're going to drop this stone. So we're going to do motion with this stone. It's dropped, which means that, first of all, of course, our acceleration is negative 9.8. Our initial velocity, since we're dropped, is 0. We don't know the final velocity. We don't know the delta y. And we don't know the time. Now, I do know that the second stone, those are question marks, by the way. I know that those aren't very pretty. We do know that the second stone is going to be dropped sometime after the first stone. So let's go ahead and call this time T1, because when I go to look at the second stone, I'm going to want to define its time T2 in terms of T1. And that will be T1 minus however long stone 2 is delayed. So for my problem, it just happens to be 410 milliseconds. That's not how you spell 410. 410 milliseconds. Oh, I don't need to put milliseconds on there. 410 times 10 to the negative 9. And yeah, so that's how you relate the two different times if they're going to be dropped at two different times. Okay, so what else is going on with stone 2? Well, first of all, we know that the mass of stone 2 is, for my problem, it might be different for everyone. For my problem, it's 6 times the mass of stone 1, so it'd be 6 times big N. And again, stone 2 is dropped. So acceleration is negative 9.8. Velocity initial is 0. I don't know V final yet. And I do not know delta y. Okay. Now I could sort of sketch a line here. Everything below that squiggly blue line there is just motion. You just do kinematics if you'd like. Yeah, for the first part of the problem, we need to find our delta y's. So you could maybe call this delta y1 and call this one delta y2, just to indicate that there will be different things going on there. And your final velocities as well, you're going to want to indicate that you have different final velocities, velocity 1 and velocity 2. But I trust that everyone can do the motion here, do the kinematics, and solve for your delta y's and your velocities. Just had a question in the chat. Why did I multiply by 10 to the 9? It's 10 to the negative 9, Nina. And not just because my time was given in nanoseconds, not milliseconds. So that was actually incorrect there. Milliseconds would be 10 to the negative third. Thank you for that correction. Yeah, you got it. All right, so you would do your kinematics. You'd relate acceleration, initial velocity, delta y, and time. So the equation that relates those, as a reminder, delta y is equal to the initial t plus 1/2 at squared. And you'll get two equations. They'll both have t1 in them. And yeah, you'll be given the time actually explicitly. So in my problem, I'm told in part A, I'm told what T1 is. So part A will tell you T1 is equal to, in my case, 190 milliseconds. And so you plug that in and solve here for your delta y's. Now let's say that you have your delta y's. So you'll know that delta y1 is something like -6 meters. And you'll know that delta y2 is something like -4 meters. And we know from the last page that mass 1 was just that big M. And we know that mass 2 is 6 times big M, because I said it's 6 times as big. Now, how do I actually find the position of the center of mass? For that, I know how to do this, right? I just need to do the y center of mass calculation, which is the sum of m times y divided by the sum of the m's. So for each mass, for my first particle, 1 has a mass big M, and the delta y that I solved for is -6. And that's meters. Meters is the units. Feel free to leave the units off. And then I need to add my second particle, which has a mass of 6 times big M, times that location, which is -4. Divide by the sum of the masses. Big M plus 6 times big M gives me 7 times big M. Let's just go ahead and add these together. -6M plus -24M gives me -30M. And then I have divided by 7 times big M. And whatever that gives you, what is that? 4.2 on 7, whatever that is. 4. Call it 4.3 meters. And that's, of course, a -4.3 meters. For part B, where you need to find the speed of the center of mass, it would be the same calculation. You do your kinematics to find those final velocities, and then rather than doing the position, if you wanted to find the velocity center of mass, you do the sum of the masses times the velocities divided by the sum of the masses. And you wanted to find the acceleration center of mass, you could do the same thing. Find any center of mass. Somebody asked me to go back to the last slide, so let me go ahead and do. There you go, Christina. Tight. All right, no problem. Rolling right along. Let's do another one here. Motion is going to be kind of a common one. Of course, we can solve motion problems now with conservation of energy. Projectile motions, explicitly, we can solve with conservation of energy. In problem number 3, we have a shell that is shot at an angle with an initial velocity, a very common setup that we had before for a projectile motion problem. It's shot from the ground with some initial velocity at some angle theta, and it flies through the air. But at the top of the trajectory, or in other words, at the maximum height up here, there's an explosion, and your particle blows in half. One half of the particle falls directly to the ground. The other half of the particle continues on this trajectory. So what we in essence have here is we essentially have 3 different problems, or like sub-problems. First, we have this projectile motion up to a maximum height at the top of the trajectory. That's something that we've done before. That's old stuff. The second problem is the explosion when this thing blows up. That's going to be new physics, new for us, physics. And then the third part is another projectile motion problem where half the fragment flies away. So the first part and the third part, I trust that you can do. For part 1, that's going to be max height. Remember, we can do kinematics to find max height. We also last week learned how to do conservation of energy to find max height. And problem 3 is just a projectile motion problem to find our delta x, right? Now, what you will actually be solving for when you find the maximum height is the maximum height will tell you the initial position, the initial y position of the projectile motion. The new part that you need to do, Brian, to answer the question, Brian just asked if we can do the range equation for 3. The range equation requires that you start and end at the same y position. Although we are technically starting and ending at the same y position, we have an explosion in the middle, so the range equation isn't valid. The general answer for the range equation is that it's very, very rarely useful. It has to be a very specific problem type. And since you have it, they usually don't even give a problem that you could solve with the range equation. Okay, so yeah, so the only, as I mentioned, the new part of this problem is part 2. So part 1, you'll find the max height, which will be your delta y that you'll carry into into the part 3, the projectile motion. The other thing you need to solve part 3 is you need the velocity for this particle. You need the initial velocity, in other words, the velocity after the explosion. So for 2, the explosion, what we're after here is the final velocity of the explosion. Okay, so I have a shell. My shell is moving with this initial velocity at this angle. Since I'm up at the max height, I know that my velocity there is just entirely the x component of that initial launch velocity. So that velocity, that speed, will just be v initial times cosine of the angle theta, whatever it happens to be. And we can call, let's call this, we need a subscript for this speed. Let's call this v sub b for before the explosion. What we're after then, maybe I should say here, what we are after is v sub a, the velocity after the explosion. So we have one particle initial and we have two particles afterwards, one particle before, two particles after. So velocity after for one particle, for the particle that falls to the ground right here, this thing is going to have a velocity afterwards of 0. It just drops straight to the ground. And so what we are really after is the velocity after for particle 2. So I have the setup here. I've sort of talked through the setup, and I haven't actually talked about how to do the new physics just yet. So this is where we'll do it. But I just want to sort of point out that you can at least get to sort of a place where you know you need to do something on that explosion. So what do we do on the explosion? The explosion, the only tool that we have that we can use is something called conservation of momentum. Last week we had conservation of energy. Here we have conservation of momentum. Now, one note that I'm going to make now that I'll repeat a few times is that conservation of momentum is more fundamental than conservation of energy. What I mean there is that conservation of momentum applies in more situations. You need a very specific type of explosion or collision in order for conservation of energy to apply. But in any explosion or collision, conservation of momentum will apply. Okay, so let's review what momentum is. First of all, we use a P for momentum. It is a vector quantity that's defined in terms of the mass times the velocity vector. Since it's a vector quantity, we can do momentum in the x and the y and solve them independently, which we will need to do at some point. The conservation of momentum looks very similar to conservation of energy. P initial is equal to P final, essentially. That's pretty straightforward, right? Now, in terms of this problem, and in general, the actual difficulty is in finding your total momentum of a system initially and finally. So my total initial, my initial, remember we're calling initial before here and we're calling final after, before and after the explosion. My initial momentum is just that entire rocket, the entire shell, which we'll say has a mass m, moving at this initial speed. So we'll just do mass times velocity. Okay, so that is just m times v initial cosine theta. Now, what about after the explosion? After the explosion, I have two pieces. They have equal mass. So each of them will have a mass m on 2. And I know one is moving with no speed, and I know that I want to find the other speed. So let's go ahead and calculate the momentums for each. We have a mass times a velocity for each. For particle 1, it has a mass m on 2. And I've said explicitly it's not going to be moving, so that'll be a velocity of 0. Nice, that's going to go away, in other words. We'll add to it the second particle, which is m on 2 for the mass, and whatever v sub a2 is, that is what we are actually solving for. So we'll leave that as an unknown. All right, so the first term on the right-hand side, as I mentioned, goes to 0. We could cancel out a mass as well from these two terms, and we have v initial cosine theta is equal to 1/2 times velocity after for the second particle. Right here, you can solve for the velocity for the second particle. As I mentioned, that will also go into your projectile motion for the third section. And then in that section, you want to use your initial height, which comes from the max height in the first part. And you want to use this as your initial velocity, which is all going to be the x velocity. So you can call that v sub x. And then you will solve for delta x in that problem. One thing that I will note is you'll see that if you were to multiply both sides by the reciprocal of a half here, you'll see that the after velocity, the velocity after the explosion, is twice the velocity of the entire shell before the explosion, which sort of makes sense. If you split something in half and you give zero velocity to one half of it, the other half should double in velocity in order for your momentum to remain conserved. Okay. So this is sort of the crux, by the way. The conservation of momentum is the central portion of this chapter. We have a few different ways of looking at momentum. One of them is to look at this thing called the impulse. So during that explosion on the last page, we had an impulse. And this will be problem 4 eventually, but let's talk about impulse. Impulse is another vector quantity. It's called J. Whoop, that's probably too big of a J. It's called, okay, I don't know how to do it. There, that's better. Impulse is a vector quantity J, and it is defined as the change in the momentum. So here's when they would ask for an impulse. They would ask for an impulse, for example, in the last problem during that explosion, they could say, what was the impulse given to the particle that went flying off? And so you could just do the final momentum of that individual particle minus its initial momentum. Nina, it's a maximum height problem. That's where you need to find the delta y. So you should have enough because you have this initial velocity at this angle theta. So that will give you v sub x and v sub y initial. And then you also know the acceleration is negative 9.8. And you know that, remember, if we're going to max height, v final in the y direction is going to be 0 as well. So you should have enough there to solve for delta y just for from the ground up to the point of the explosion. And again, you can also do conservation of energy. Okay. Oh, cool. Okay. Yeah, so as I mentioned, impulse is just change in momentum. It's just a correlated sort of quantity that you typically don't have to do impulse, like a whole bunch of extra stuff. It's usually just an extra step to find the impulse. Now, you can also, because we know momentum is mass times velocity, you can also say that the impulse is the mass times the change in the velocity vector. So that is usually an easier calculation than doing the change in momentum. Usually you'll do mass times v final minus v initial. There's another definition for the impulse, because in order for an impulse to be imparted on an object, there is implicitly some force which must be acted upon the object. So we can also relate the impulse to the average force of like a collision or explosion times the time that it is imparted on the object. So m times delta v is equal to F average times delta T. They're usually pretty clear when they're asking about the average force. They'll ask pretty explicitly. One thing that I will note that you are responsible for in this class, because it's physics with calculus, is that technically this last definition here comes from the fact that the impulse is the integral of force with respect to time. So just to write that sort of over here, J is the integral of the force vector with respect to time. We will, if you do need to use it, I don't even think we have a homework problem where you do need to use the integral definition. If you do need to use it, keep in mind on the last week and on the first exam, typically when we're doing an integral, we will either be explicitly given an equation or we'll be given a graph where we have to read the area off the graph. That tends to be the only way that they ask us to employ integrals in this class. Okay, so yeah, so problem number 4, as promised. Problem number 4, you drop a ball and the ball bounces. Pretty straightforward. It's going to go down. For me, it goes down at 18 meters per second, and then it comes back up at 14 meters per second. Notice that it doesn't rebound with the same speed that it hits the ground. That means that we have an inelastic collision, which means conservation of energy does not work for the actual bouncing off of the ground. But we can still find the impulse. They gave us a mass explicitly. We can find the impulse right here, mass times the change in velocity. One thing I will note is that if your ball is traveling downward, keep in mind that means it has a negative initial. So if I were to do my impulse, I would just do m times delta v, which would be the mass for me is 1.7 kilograms. And then I just do v final, which is 14, minus v initial, which is negative 18. So I have minus a negative. And whatever that would give, what is that? 32 times 1.7. What is that? About 50? Very roughly about 50. What are my units for impulse? Kilogram. Oh, excuse me, sorry. Kilograms for the mass times meters per second, if you'd like, or Newton seconds, Newton's times seconds. Where does that one come from? Well, that comes from my other. Let's see if I can get a second in here. It's never going to allow me to write all the way over on the screen. There we go. Newton's times seconds comes from force times delta t. For the second part of this problem, they give you a delta t and ask you to find the average force. So you just relate this 40 newtons per second to the other definition for the impulse. All right. Problem number 5 has quite a convoluted setup. Now we're kind of taking the training wheels off a little bit. We're incorporating impulse and conservation of momentum into some other problems. So in this one, there's a person that's going to sit in a chair and someone pulls the chair out and the person free falls to the ground. And we're asked to find the impulse and the average force. So of course, we know that our impulse is m times delta v, and oops, m times delta v, and that's the average force times delta t. So part A, we'll find m times delta v, and then in part B, we'll just relate that to the average force. Okay, so the question here, though, is in finding my m times delta v, I have m times v final minus v initial. I'm finding the velocities relative to when this person hits the floor. So if I'm going to hit the floor, that means that my final velocity is going to be 0 because I'm going to come to rest on the floor. And so v final, well, let me just write this off to the side. V final is equal to 0. But the question is, what is my v initial? So far in this class, the initial has meant before some projectile or before some motion or something like that. Now what we're talking about is we're talking about an actual collision. So my person, let's see if I can stick figure this person. He's falling and screaming. We know that this person is going to fall. In my case, it's half a meter. So he's 0.5 meters off the ground. And the implication here is that he's in free fall. But there might be, your intuition to this point in the class might tell you that your initial velocity is like before the guy starts falling. Actually, what it is going to be his velocity when he hits the ground. That will be your initial velocity for your collision. I might be sort of harping on a point that I don't need to, but I just want to point that out. So what we need to do is we need to find out the falling motion. This will be part 1. And then we can actually calculate our impulse in part 2. So part 1, when the guy is falling, here you can do, again, you could do just regular projectile 1D downward motion, or we can do conservation of mechanical energy. If I choose to do conservation of mechanical energy, which I would, I'd say that I have some potential energy initial that I'm turning into kinetic final. My potential initial is mgy, and my kinetic final is a half mv squared. Cancel out my m's, and this will give me that v is equal to root 2gy. Cool. They give me my y right here. I know that g is 9.8. I plug those in. That will be my v. And then, of course, this is going to be your v initial. Once you have this v initial, then we can go to part 2 and evaluate the impulse directly. And then for question B, we just need to relate this impulse to the average force. Okay, now there's a few, I think this is actually kind of in a row that we have. Oh no, we have the balloon problem in the middle. But as I mentioned, we're kind of building up here. I think that last problem hopefully was pretty straightforward. Now the problems are going to get a little weird. Some kind of convoluted setups in some of these problems. So this problem, you have two blocks connected by a spring. Why? Who knows? Who knows why you would set two blocks on a table and connect them by a spring? What you're gonna do is you're gonna push them together, and then you release the blocks, and the spring is gonna push them away. And what do they give us as far as the setup? They'll give us the masses of each block, and they tell us that one block has a certain release speed relative to the floor, and they want to know how far the other block travels. And then they switch up the way that they give us the relative speeds. So what this problem is really sort of trying to drive home here is the idea of reference frames and paying attention to where a certain speed is given in terms of. So is it given in terms of the ground? Is it given in terms of the other block? Is it given in terms of the spring? For part A, they'll just give you the speed of block L explicitly. And my problem, that happens to be 1 meters per second. Now keep in mind that block L is going to move to the left. So my 1 meter per second will be -1 in the x direction. And then that's kind of all I need to do. So these guys start with no momentum because they're at rest. So when I go to do my conservation of momentum, momentum initial is equal to momentum final. My initial momentum, since they start at rest, is just 0 because there's no speed. My final momentum for each, I have the mass of the left one times the velocity of the left one plus the mass of the right one times the velocity of the right one. And I know I'm kind of doing this one by one here, but my mass for the left one is 1.2. My speed is -1. My mass for my right one is 0.7. And I'm solving for v sub r. This negative, I'll have -1.2, and then I add it over, divide by 0.7. What will that give me? 1.2 on 0.7 is roughly a v sub r of, say, 0.6 meters per second. The sign here matters. I do get a positive velocity, which tells me that block r is moving to the right. I knew it needed to, but it's still nice to get the confirmation from the equation that I did this right. And ultimately, I think we want to know how far it moves in a given time. Well, it's constant speed. So for that, you can just do delta x equals velocity times time. You have your velocity now here. And if they give you a time, then you can solve. All right, so that's part A. Part B, they switch it up a little bit. In part B, the speed of block L is given in terms of the speed of block R. So that means that my 1 meter per second, that was all velocity in the L direction, is now going to be the difference between the speed for R and the speed for L. That's what it means when they say it's a speed relative to R. So that means that, in sort of dummy notation here, so I don't know if that's a bad term to use, but instead of having v sub L is equal to -1, now what we would have, let me make sure that I stick this landing here, is that v sub L is v sub R -1. So why do we do this? Because we're given that we have the speed of L is 1 meter per second to the left relative to the velocity of R. So you have to add in the velocity of R. That might be a more intuitive way of writing this, is that our v sub L is still -1, but then we have to do plus v sub R. Now, when I go to do conservation of momentum, we still do the same step here, but when I go to fill in my equation, I have now 0 equals m sub L, which is 1.2, times -1 plus v sub R. And then I have plus 0.7 times v sub R, just like I had over here. And then I go ahead and solve this equation. What will this give me? -1.2 plus 1.2 v sub R plus 0.7 would be 1.9 v sub R. Nope, nope, I do not want that. And then, of course, this is equal to 0 on the other side, whatever, and you solve from here. V sub R will still be positive. Now it'll be 1.2 on 1.9, which is, I don't know, 0.63 or something like that. Meters per second. At any rate, then it's still the same. Delta x equals velocity times time in order to find the displacement a given time later. Okay. All right. And there's a lot to this week. These are quite involved problems. Okay, problem number 7. Problem number 7 is a balloon problem. You got a guy climbing a ladder that is hanging from a hot air balloon. And initially, this hot air balloon is just floating here. Let me draw a very, very rough looking sketch there. And here's my ladder. Beautiful. And there's a man who I will model as a box or a single particle. And this entire system, the entire thing, has a speed of 0. It's not moving relative to the ground. It's just sitting there, it's just floating in the sky. What's going to happen, though, is that this guy is going to start climbing upward. And as he's climbing up the rope ladder toward the balloon is going to start moving down. Now, here's why. The reason that the balloon moves down is because the center of mass of the balloon man system has to continue moving at 0 meters per second. When he moves, he's going to move the center of mass upward, right? Like, think about it in terms of just, let's say that they weigh the same. You have the balloon that has a mass m, you have the guy that has a mass m. Where's the center of mass of these two things? If you add them together, we know that the center of mass, if they have the same mass, would just be somewhere in here, okay? Now, when my guy moves upward from this point to, say, this point up here, that center of mass should transition to a higher position because it's still going to be in the geometric, average between the balloon and the man. But since we want to keep the speed of that center of mass equal to 0, that's going to cause the balloon to move downward until the new center of mass of the system is in the location of the old one. All right, so that's a very technical explanation. A maybe more sort of basic way of looking at this is that how's a more basic way of looking at it um, is just that conservation of momentum, I guess, is another way of looking at it. Maybe this isn't a basic way, but a more physically intuitive way to look at it is just that I have my initial momentum is equal to my final momentum. What's my initial momentum for the whole thing? Well, I know in both cases it'll be mass times velocity, right? So what is my mass? It's the mass of the balloon plus the mass of the man, but I know that the initial speed is 0. So that initial momentum is 0. What is my final momentum? Will be the mass of the balloon times the velocity of the balloon plus the mass of the man times the velocity of the man. Since the left side is 0, if the velocity of the man is not 0, then the velocity of the balloon has to also be not 0. And if this is going up, if this is positive, this has to go down, excuse me, or be negative. Okay, so that is the explanation generally for why the balloon moves. Hopefully, I might be a little overwrought in my explanation here, but I think it's important to understand the concepts. Now, as far as the actual calculation, we're going to be given a speed of the man relative to the ladder. So we're not given his speed relative to the ground because he's not climbing from the ground, he's climbing the ladder itself. So just as we did in the last problem, when we said that the speed of block L, when given relative to block R, we had to add in the speed of block R. Well, we have to do something similar here and say that the speed of the man is equal to my speed is 0.55 meters per second. So the given speed plus the speed of the balloon. Make sure that I've got my signs right here. Yeah, this should be okay. So let's go ahead and solve from here. Let's see if we make sure we get the right thing. On the left-hand side, as I mentioned, the left-hand side of this is equal to 0. On the right-hand side, I have the mass of the man, which for me is 57 times 0.55 plus the speed of the balloon. And I have, I guess I switched these. And then I'll do the mass of the balloon times the velocity of the balloon. My mass of the balloon is 260. And the velocity of the balloon is just v sub b. Again, I switched these two terms with the subscripts. All right, so go ahead and distribute here. 57 times 0.55. Pull up my calculator. 31.35 plus 57 times v sub b plus 260 times v sub b. Okay, and then divide by sick. Okay. Yeah, okay, so again, this is a 0 on the left-hand side, so I have 0 equals 31.35 plus 57 plus 260 is 317 times v sub b. And then solve here. I've run out of room a little bit, but if I solve this, I will get that v sub b is equal to negative 0.099, and that's meters per second. And the negative sign there tells us explicitly the answer to part A. So you don't actually need to know sort of the conceptual reason why you get that negative. All you need to know is that that negative tells you that your balloon is moving downward. And cool, there's two different ways of explaining why the balloon moves downward. And then we need to find, yeah, oh, okay. And then if the man stops climbing, what is the speed of the balloon? Well, again, remember that our total momentum always needs to be equal to 0 because we start off with 0 in the reference frame relative to the ground. So our total momentum will always be 0. If the man isn't climbing, it was only the man's climbing motion that caused the balloon to move down. If he stops climbing, the balloon stops moving too. Problem number 8. Problem number 8 is a softball problem. It is not softball because it's easy. Literally talking about a softball being hit by a softball bat. And it's a two-dimensional problem. Your softball is coming in at a velocity of 17 at a downward angle. So 17 meters per second, traveling at an angle of, for me, 47 degrees below the horizontal. And it's going to hit the bat, and there are two different, your two different parts are after the collision with the bat, it'll either go straight downward or it'll go back toward the pitcher. So I'll just do part B. Part A would be very similar. I'll just tell you where to change it. But part B, I'll work through here. So this is before. Just write that down here. This is before the collision. And then after the collision, let's say that it will be moving back toward where it came from with a speed of 18 meters per second. And I'm asked to find the magnitude of the change of the momentum. The magnitude of the change of momentum, how would that look? Magnitude of the change of momentum, if I want the magnitude of that, that's just the magnitude of the impulse, right? So I could also do force times delta t, but I don't have that. Anyway, I can still just find this explicitly because that is delta p is equal to m times delta v. Keep in mind, as I mentioned, that momentum is a vector quantity. So if I have two-dimensional vectors, I need to deal with each dimension independently. And then I need to do a vector sum at the end to add it all together to find a net magnitude. So just as we've done before, we'll split our x and y like this. In the x direction, I have my initial component of the velocity, just the x component, and then afterwards I have this this final velocity vector, which for part B is all in the x direction. In both cases, I know that I want to find the change in the momentum, which would be m times delta v sub x. You could say that this is the change of the x component of the momentum will be mass times the change in the x component of the velocity. And the mass will be given in the problem. So I just need to find the velocity before and after. So v final minus v initial. What is v final? V final in the x direction, I have this 18 meters per second, and that is traveling to the left. So that is a negative 18. And then I have to subtract the x component initially, which is 17 times the cosine of my 47 degrees. So that'll be minus 17 cosine 47. I can plug in my mass and I can solve here. On the y side, it would be very similar. Change the momentum in the y direction will be mass times the change in the velocity in the y direction. Again, mass is given. And then I just need the final velocity. What is the y component of my final velocity? Remember, this velocity is all to the left. It's all horizontal. So my final velocity in the y, the vertical, would be 0. And then I need to subtract this y component of my initial velocity. Notice that that is a downward component, so that component is negative. It would be negative 17 sine of 47. And then you solve for the number here. Now I'll leave that up to you, but the one thing that I want to note is that our total magnitude for the change in momentum, since I'll have a change in momentum in the x and a change in momentum in the y, my magnitude for delta p will be equal to the square root of delta p sub x squared plus delta p. They're not going to let me fit this. Let me try that again. The magnitude of the momentum, of the change in the momentum, is square root of delta p sub x squared plus delta p sub y squared. Okay, that's what you actually need to ultimately calculate. And just do it for the two different final velocities. Okay, two more problems here. The next one is stepping it up even more, if you can believe that, stepping up the difficulty even more. Now we have two explosions that are going to happen to this thing that is called a rocket, but is clearly 3 blocks sitting on a table. The blocks are called C. C is the center one, L is the left one, R is the right one. And they start off at x equals 0. Okay, and they give you this very long process that happens. First of all, block L is going to be shot to the right. Or, I'm sorry, shot to the left, obviously. Block L is shot to the left with a speed relative to the velocity of, excuse me, C and R, which remain attached. So for part one, you have, first of all, before I say anything, I should mention that my initial momentum for this whole thing is 0 because we start at rest. So momentum initial is 0. That'll be the left-hand side. We just need to set that equal to then the final momentum, which will be the sum. So my final momentum will be m sub L times v sub L plus m sub C plus m sub R times v sub, let's call it CR, because it's C and R moving together away. So we're still treating them as one unit, which is why they just have one momentum in the picture after the first explosion. All right, so we noted the conservation of momentum. We also know that we're given the speed of block L relative to the other two blocks, not relative to the ground. So we know that the velocity for L will be equal to the velocity that's given. They say that it's, in my problem, it's 3.2 meters per second. Most important thing is that that is to the left. So block L will be moving to the left. That means that that is a negative 3.2. And then just as we've done before, since we're given this speed relative to C and R, we have to do plus the velocity of CR. Once you have this, you can plug it in here. You set this whole guy equal to 0, and you will solve for v sub CR. Now that you have v sub CR, we can go to our second explosion. In the second explosion, let's redraw this diagram above. Now in the second explosion, we don't care about L. L has blown off, it's flown away. We just have C and R, and we know that they've moved some distance away from 0. We don't know how far. We can find it since we have the speed, and in fact, that's what you have to do in the second part. You do have to find how far it moves. But crucially here, we're concerned with the speed of block C after our second explosion. So the entire system, first of all, the entire system will be moving with v sub CR, the velocity that you find from doing conservation of momentum for the first explosion. So my initial momentum here is mc plus mr times v sub CR. We also already know what this is equal to. It's also equal to ml vl, right? But we could have some solution there. Probably wouldn't have one immediately because there's also a v sub CR right here. But regardless, we can calculate this guy. This is our initial momentum. What about our final momentum? Well, they tell us that block R now is going to be shot to the right with the same velocity, 3.2 or whatever yours is. That block R will be shot to the right. So my final momentum is going to be m sub C times v sub C plus m sub R times v sub R. And I know that my velocity for R is given as 3.2 relative to the velocity that C has after the explosion. So that means that v sub R will be 3.2. Now that is a rightward velocity, so that's a positive 3.2 plus v sub c. Once again, plug this in for v sub r, and then set this whole expression equal to this one. The masses will be given, so that's not too bad. And we will have found v sub cr in the first explosion, and we can plug that in. And then ultimately, you can solve for v sub c that way. Okay. The last problem, luckily, is not the worst problem. Last problem is a pool ball problem. You got a pool ball coming in, bouncing off the wall and bouncing back out. You have theta1 and theta2. Yeah, so Nina, for the position of center of mass, you've now found the two different speeds, and they give you, let me just double check that they do give you times. Yeah, they give you times. So the object will travel at v sub cr from time 0 to time of the second explosion, and then it will travel at v sub c from the time of the second explosion to whatever time they ask you to investigate sometime later. So like for me, it's 0 to 0.6 seconds. So it would go v sub cr for 0.6 seconds, and then you do 2.7 minus 0.6 for the other time. And then just, yeah, velocity, delta x equals velocity times time. Cool. Okay, pool ball problem, cue ball, bouncing off of the rail of the pool table. You have an initial speed and an initial angle, and they tell you that you're going to reverse your y component, but the x component will remain unchanged. So what does that mean? Well, this velocity would have an x component to the right. This is my like initial velocity, and the final velocity is going to have that same x component. So this would be v sub x and v sub x. And we also know that that incoming velocity will have some y component, v sub y. And they tell us that you reverse that y component by ramming the ball into the wall. So that would be negative v sub y. And we're asked to find two problems. The first one is, given theta1, what is theta2? Well, this is actually, I'm not even sure how to answer this explicitly other than to like prove it, but this is actually a very straightforward answer, that those would be the same angles because all you've done is reverse your velocity. So maybe what you could do is you could say, okay, I know that I have v sub x and v sub y, and then I know I'll have v sub x and negative v sub y. And in both cases, I actually want the angle off of the, let's see, those are my resultant vectors. Here's my incoming angle. This is my outcoming angle. So I want to find this angle theta2 in terms of theta1. And I know that tangent of theta1 would be the opposite, which is v sub x, over the adjacent, which is v sub y. And if I want to find the tangent of theta2, the opposite would be the same length as v sub x, and the adjacent would be the same length as v sub y. I'm not even sure that I think I'm just kind of going in a circle. But the point here is that, yeah, that these angles 1 and 2 have to be the same. You'd have to change the actual size of v sub y, of the y component, in order to change the angle. I think I'm maybe chasing my tail too much here. I think that's probably straightforward. Okay, second part is we want to find the change in the ball's linear momentum. So we know that, and again, magnitude of the change in momentum. Remember from a few problems ago, the magnitude of the change in momentum is equal to the square root of the change in the x component squared plus the change in the y component squared. So what is the change in the x component? First of all, it'll be mass times the change in the velocity, but we are told explicitly that the velocity does not change. So delta v is 0, therefore delta p is 0. So we just need to find the change in the y component of the momentum. Oh, and that square root of a square is just going to give you, yeah, the change in the y component of the momentum. So let's go ahead and find it. The change in p sub y will be m times delta v sub y, which will be equal to m times v sub y final is negative v sub y minus v sub y initial, which was positive v sub y. So we've done a little bit of pre-work here to say this is just negative 2m times v sub y. And then the only thing that we need to do is find v sub y. I think I'll leave that up to you. You're given the initial speed and you're given the angle theta1 right here. You have done this a million times where you found a y component, you plug it in here. Remember that they ask us for a magnitude, so I've left the negative sign out in front, but ultimately you just take the absolute value there. And that's it. Cool. Okay. Yeah, that'll be it. If you have any questions, feel free to stick around. And that's it for this week.
Thank you.
Yeah, no problem.